So let me go on to the part 2. Okay. All right. So all right. So let's go to part 2. In this one, I'm going to really focus on one particular example. So I've given you the data sets and so on and so forth. So the many surveys really rely on the self-report of diseases. The question is, how accurate are these reportings? And especially you want to know, are there any kind of segments of the society that are accuracy differ? So NHANES is unique because it allows examination of this aspect. So NHANES asks self-report of diabetes. So 1 means no, 2 means they're pre-diabetic. They've been told that they're pre-diabetic. 3 means they were told that they were moderate. And 4 means they're definite, that they have been told that you are diabetic. And if 2, 3, or 4, then they ask, are you using medication? Are you taking insulin or are you taking pills? But NHANES also measured the fasting glucose and also in the lab portion, and then hemoglobin A1C is also in the lab portion. So the lab portion, they have a fasting glucose and hemoglobin A1C. So question of interest is that what is the population proportion of undiagnosed diabetes, undiagnosed diabetics? So the people who said no in the self-report, but then somehow based on the fasting glucose, hemoglobin A1C, that they would be classified as diabetic. And what is the relationship between the SES and being undiagnosed? So SES, I'm measuring here using 3 variables: education, marital status, and poverty status, and age and gender or additional covariates or confounders that you want to adjust for. So this data set from 2017 to 20, so it has a 9,232 people with 20 plus. And then these are the variables I've given you in the data set. There are 2 additional variables which I'm not using it, but that's in that actual data set. You have 2 additional variables that they ask if you say that yes, a doctor told me I have pre-diabetic or moderate or diabetic, then they ask, when was the last time did you have a test for A1C in the past 12 months? And if they say yes, then it says, what was your A1C value? So those are additional complications, and I haven't included them. Initially, I included them, and I thought I included too much. So the code and data sets are as Paul says, that they are available in that website. So IVEware, I use the IVEware to implement the multiple imputation analysis. So as I said, it uses a sequential regression multivariate imputation. You can use it as a standalone or in conjunction with SAS or Stata and SPSS. Now, the easier way to create, because sometimes I want to use SAS for some, or for some, Stata for some, because there are different routines, complete data analysis that I want to use. Like a SAS has a good, some of them, Stata is a nice thing, nice features, or as graphical features and so on and so forth. So I tend to mix all software packages. So best way is to create an XML file where it can toggle whether you are using SAS or R or Stata or SPSS. So IVUware takes the SAS, executes in SAS, takes the R, executes in R, takes the Stata, executes in Stata, and takes the SPSS and executes in SPSS. So it's kind of a nice feature that I don't have to be tied to any one particular software. I can use it for any of the sources mixture of software packages. Now there are other ways of running the program within. If you say, oh, I'm only SAS person, then you can run IVUware within SAS, so kind of or within R or within Stata or within SPSS. So if you're one software person, then you can run it in that one. So there's a manual that talks about how to run it and also in my book I also talk about that. The second book, Multiple Imputation in Practice, talks about various examples. And can be used to perform complex survey analysis, accounting for stratification, clustering, and weighting. It works in Unix or Linux and Windows and Mac operating system. It is organized by these different modules. The impute is used for creating multiple imputations. Describe is used for doing descriptive analysis. Regress is for doing regression analysis. The BB design creates the non-parametric synthetic population. Synthesize is for the disclosure limitation. It creates a parametric or non-parametric synthetic populations. Combine is a module that uses, say, if you have 5 different data sets, you want to bring them together, and then you want to align them by variables, and they are stacked up so that they are kind of aligned by the variables. Then combine is a feature that allows you to do that. SAS mod uses a variety of macros in SAS to do a complex survey analysis. So, for example, if you want to do a structured equation model, and you can use ProcCalis, but complex survey design for doing the complex survey data analysis of a structured equation model. But using this toggle feature, you can practically use any command in R or Stata or SPSS or SAS to execute that command from that package. So I've given you this one file I gave you later on, proc mi analyze. So all the files are in the data set. So this is a kind of a description of what this thing is. So I won't go through the more. I don't know how many of you have used IVUware before. This is the kind of a structure of a XML file. So here I'm toggling SAS. So SAS name as SAS output that tells IVUware is that toggle SAS, and then all the commands that you give will be saved in this output file, SAS file, and then there will be a log file, and then there will be a LST file that created based on that SAS run. So that toggling of SAS just says that, okay, now start the SAS job. So I'm just reading in the data set. This will be very familiar to people who are using SAS, libname workshop, and then I'm copying into a data set. Now the next set of commands is sort of impute commands. So I'm toggling impute, and then I'm going to say, well, save all the output into the SAS imp out directory or SAS import files. It creates again the SAS file, set file, log files, and LST files. So data in is a command for saying that which data is being imputed. So it will take automatically. If you have multiple data sets, you can say which one is to be imputed. Data out says that which data, what is the name of the data file that you want to save. the imputed data to be. All means that it will stack up all the imputed data one below the other. So sometimes it is useful to stack up all the data. Otherwise, the way it will store is that it creates an efficient data. Is that one imputed data set, and then it says row number, column number, and what the values are. So it's kind of a way to save the file. And default is categorical. They said that if I didn't say anything about any other variable, treat that as a categorical variable. So it will automatically create dummy variables whenever it is included as a predictor in the model. And it will be used as a logistic or multinomial logic model, depending upon how many categories it has, when it is used as a left-hand side variable in the imputation model. And then I have to specify what the continuous variables are, the glucose and A1C, age, and I'm using weight as a predictor variable here. So the weight is also treated as a continuous variable. Now there are some additional variables there. I don't want to do imputation, or I don't want to use them as a predictors. So that's the ID number. I don't want to use them as a predictor anyway. So I'm transferring the ID number, and then I'm also transferring the cluster variable. And then these two variables I'm not using. The A1C SR is the self-report value of A1C for those who said that they have they are test for A1C. So if they say that, yes, I was tested for A1C in the past 12 months, then they will be asked, what was your self-reported value? That restrict says that there's a variable called med-s, which is only asked if they are pre-diabetic, diabetic, moderate diabetic, or diabetic. So that means that the med-s has to be imputed only for those people where the diabetic self-report is greater than 1. So IVE-WARE then automatically will fit the model only for subset diabetic SR greater than 1, and then impute the values for the med-s. Here I'm saying iterations 10, multiples 10, and then I want to create diagnostic plots for these two continuous variables, glucose and hemoglobin A1C. And then I want to use a seed, because the seed is important, because I want to specific, because all random draws, I want to reproduce them later on. So specifying the seed, make sure that it's replicable. So when I run, 3 months later, when I got a review, and then they said, you need to include these variables, I want to make sure that I'm using the same seed. Then impute is ending. The toggle, the impute is ended by the standard XML language, that caret / impute close caret. It gives you the toggling of impute is complete. So then as soon as it sees that, then IVE-WARE then is ready to execute that portion of impute module and then get the results. Now, once I have imputed, then I'm creating the post-processing of the stacked imputed data set. Now I have to create this new variable undiagnosed in the data set. So if the now there's no missing values, so undiagnosed is 0, setting it as 0. But if the diabetic self-report is 1, that means that they said that no, the doctor did not tell me that I'm diabetic, but their glucose level is greater than 126, or their A1C is greater than 6.5. That means they are diabetic, actually. So based on their clinical measures, they would be classified as a diabetic based on the American Diabetic Association guidelines. So then the undiagnosed is 1. So this is a new variable I've created in the imputed data set using the combinations of the variables So I'm just doing a proc means for the undiagnosed weighted mean. So for you to do the analysis, I store them in a workshop imputed data file, which is I've given you that also so that you can do the analysis of that. Now this is stacked up data, but in order to do the analysis, I need to split them into 10 data sets. So I wrote a small macro for splitting the data set into the 10 data sets, because I've done 10 imputations. And then the IVUware creates this system variable called underscore mult underscore, which tells me which imputation it is. So if mult underscore is 1, that means it is a first imputed data set, the second imputed data set. That's what I'm using to create the split of 10 data set. Now the regress command, I'm toggling now regress command in the module in the regression, where I'm doing the, now I want to do the multiple imputation analysis of this 10 data sets. So I've listed all the 10 data sets to be analyzed. So here the categorical variables are education has 4 categories, marital status has 3 categories, poverty has 3 categories, undiagnosed is also categorical variable. So when in the regress IVUware will automatically create dummy variables. And then the dependent is undiagnosed, because that's what I want to use. And then reference is to 0 as a denominator value. So the undiagnosed 0 is the reference categories, undiagnosed 1 is a numerator categories. That's kind of a proc logistic descending feature. Now, when you say categorical education, automatically it will create the last category as a reference category. But if you want to change it, then you can specify within the like a parentheses which category you want to be referenced. So, for example, if you say less than high school is to be referenced, then you can specify ED bracket 1 close bracket. Then it'll treat 1 as the reference category, and then it specifies what are the predictors, age and female, education, marital status, poverty are the predictors. Link is logistic. It says, well, I'm interested in logistic function. Then you specify the design variables. So your stratum is SDMV strata, cluster is SDMV PSU, weight is the interview weight, and then just run the regression. And then I'm closing out the regress command. Now IVUware now is ready to run the regression command. Now I think I need to close out the SAS because I'm done with SAS. So now when you click run, it'll automatically invoke SAS, then run the impute, run the regress, and then pipe all the output to the appropriate files, and then it'll exit the program. And you can use so here is the what it does is that it gives you sort of a summary of how many observed values are there, how many imputed values are there. And now the double counted is a feature that we added because sometimes there is an error in the data set that we may not have detected. So for example, Med-S, the medication yes, is asked only if they are pre-diabetic or moderate diabetic or diabetic. But sometimes in the data set, we might find that restriction is not satisfied. So somebody who said diabetic self-report is 1, that is, they're not diabetic, but then they said, yes, I'm taking medication. So that's inconsistency. So then double counted means, hey, you asked me to restrict it, but by the way, I'm double counting it because your data set, actual data set, doesn't satisfy it. Although I'm satisfying the IVUware satisfying it in my imputation process, but be aware that your actual data set does not satisfy the restriction that you are asking the IVUware to impose. So it's kind of a diagnostic purposes. Anything is not 0, that means there is some problem in your data set. So you may want to check that variable and see, make sure that you edit it and make sure that you have a we have sometimes very complicated restrictions you apply, and then there is an error in the data set, then you want to know that there is an error in the data set, and that's why the double counted is being used in that context. For most of the problem, simple problem, that always will be zero, but if it is not zero, then there's some problem in the restriction statement. And it also gives you the observed and imputed distributions. Now, by the way, I also wanted the so here I'm also saying the bound statement for the A1C and glucose. So I'm saying that the bound should be kind of a legal range of what is possible, clinically plausible. So it should be greater than or equal to 2.8, but less than or equal to 16.2. The glucose should be greater than or equal to 47, less than or equal to 451. So these are sort of a legal limits, and these are also satisfied in the observed data set. So you can say that you want to put the bounds on those, so it will automatically draw from the truncated distribution, satisfying those bounds. So it gives you kind of a your observed and imputed data set, and also combined data set. So for example, the hemoglobin A1C is being imputed for 1,151 people, subjects. So the imputed range ranges from 3.2 to 10.2, and observed range is 2.8 to 16.2, and then the combined range is 2.8 to 16.2, and it gives you the mean and standard deviation for the observed, imputed, and combined samples. So you can see that the distribution looks pretty similar across both observed and imputed data set. Now, MED-S was a restricted variable. So you say that it should be only for people who said that they were told either pre-diabetic or moderately diabetic or diabetic. So it creates a new category 2 for those people, for whom the MED-S is not applicable. That's the 2. The new category is created. That's a non-applicable group. That's not in the observed data set, but that's only in the imputed data set. So there are 6,635 people who have diabetic self-report equal to 1. For them, the medication value is not imputed. But in this case, it shows that everybody is imputed to being on the medication use. So it's kind of strange that you should have seen some people who said no. But if you look at the observed data set, so there are 862 people who said that they were pre-diabetic, but 52 of them, they said they were missing their medication use. But among those people who answered medication question, 52 said yes, 0 said no. Same way, the people who are moderately diabetic, there are 206 people who didn't say anything about medication use. 56 of them, they said yes, they are taking medication. None of them said no. So based on this data, it seems like, I think what we were thinking is that almost everybody is using medication use. So they're all imputed to be medication use. There are only 3 people with missing values who said that they were diabetic, self-report diabetic, and 223 of them, they are not taking medication. 1,194 of them are taking medication. By random draw, all 3 are also being imputed as 1. So based on this data set, these 2 kind of data, no one said they are not taking medication, implies that we were thinking that all these 862 should be imputed as having medication. That's why you are getting this kind of a lopsided distribution. It's kind of reflecting whatever data set is there in the observed data. So these are the diagnostic plots. So here is the diagnostic plot of the observed and imputed values. And you can see that there are few, these are the people who said that they're diabetic, but they didn't go in for lab. So their values are imputed high. And so you can see that the distribution looks pretty similar. That's why here is the histogram of the residuals after regressing on the propensity score. These two residuals should be very similar if the imputations are good, but you can see that there's a bunch of people who are being imputed the higher values of the values. So there are some people who are. So, and again, a lab is showing up. There may be some selection bias in the lab values of people who are coming into the lab values. So glucose, I think, looks pretty similar, and you can see the distribution kind of overlap between the two. So people who give fasting versus the people who gave the hemoglobin A1C only, the more different people. So that's what is reflected in the imputation process. Now, if you do a regression, then this automatically, this is the output from the regression analysis. Logistic regression is being used. Undiagnosed is the dependent variables. The predictors are age, female, education, marital status, and poverty. It also tells you what are the reference categories being used. Education is 4. So 1 means less than high school, 2 means high school, 3 means some college, 4 means completed college. Marital status is 1 means married, 2nd is separated, divorced, widowed, and 3 is never married. Poverty is the low poverty, 2 is the second poverty level, 3 is the higher the least poverty level. So undiagnosed is the dependent variable, and then the stratum variables are given, and it gives you sort of an estimate. So this is a dummy variable for education being equal to 1, the dummy variable for education 2, and so on. So you can see that none of them are kind of significant because it's so highly clustered. Design variables is it's about 8% are undiagnosed. So there's a power issue, but still there's a gradient across the education with 0.33 as a regression coefficient, log odds ratio for education 1 compared to the education 4. It also gives you the odds ratio, and then it gives you the confidence interval for the odds ratio as well. So if you are in education 1 category, you are 39% more likely to be undiagnosed compared to the people who are completed college and so on. So marital status is not that. So compared to never married, the married are slightly less likely to be undiagnosed. And compared to poverty level 3, both of them are highly likely to be undiagnosed. So it's kind of gives you kind of a regression output. It also calculates the design effect. You can see there's because of the heavy clustering, there's a lot of design effect here. It also gives you what the SRS estimate. If you had ignored the sample design, what is the estimate you would have obtained? And then what is the percent difference between the SRS estimate versus the design-based estimates? You can see that the design-based estimates, simple random sample estimates, are quite different from the design-based estimates. So here, the clustering, weighting is important. Weighting and stratification are important to be incorporated in the analysis. Now, you can do the same analysis using proc-MI analyze rather than regress command in IVE-where. So here I'm just reading in the, this is totally SAS. So here I'm reading in the SAS data set, which was the imputed data set, which was stored. Now, if you do a survey logistic, if you use a class variable, it uses 1 - 1 coding rather than 1 0 coding. So in order to be kind of a consistent, you had to create the dummy variables. I prefer anyway to create the dummy variables in my analysis rather than class variables. So because 1 - 1 sometimes is harder to interpret than 0 1 variables. So I'm just creating the dummy variables for the education, dummy variables for the marital status, dummy variables for the poverty status. I'm sorting by imputation. Now, MI analyzers uses a different keyword than what IVE-where uses. IVE-where uses _mult_ for separating the imputations. So whereas SAS proc analyze expects a _ imputation _. So I just copied it in order for SAS to be satisfied. So proc survey logistic, and then I do a cluster strata weight, which is very similar to what IVE-where. And then the model is undiagnosed, descending, which says that the 0 should be taken as a reference category and 1 should be the numerator category. Then this is all education, all the predictors, linkers, logit, and by imputation. So this is kind of does the analysis, complex survey analysis for each imputed data set. It outputs the parameter estimates, which is then used to combine. So if you use the combine features, is a proc MI analyze, then take the parameter and then say that, okay, these are the parameters to be combined. Then it combines and gives you the output. Now, nice feature, there are some nice features in the proc MI analyze output. So the point estimate, it should be exactly the same as what we got in the regress, which is exactly the same. The standard error might be slightly different because the proc MI analyzes using these Taylor series, whereas the regress uses the jackknife. So therefore, the methods might be slightly different, but they're pretty similar. It gives you a 95% confidence interval, and it also gives you the degrees of freedom, and then what was the minimum and maximum, and then it gives you the t statistics, and then what the p-values are. But nice thing also, it breaks down the between and within variance, and it also gives you the fraction of missing information. And you can see that the fraction of missing information is that, so you can see that for age, it's not much missing information, but for some of them, it's a huge, considerably large fraction of missing information. The missing for females being 66% missing information, and so on. So this gives you kind of a feel for how much information is because of imputation. So it gives you kind of a relative increase in variance of relative efficiency as well. So it gives you kind of a little bit more diagnostic than regress. So it might, if you are using SAS, I think probably proc MI analyze, you can use proc MI analyze or regress. So here is the command for doing it in R. So exactly it's the same kind of a structure. I'm toggling R, and once I toggle R, then I suggest a set working directory, and these are the libraries that I'm going to use. Heaven is the one to read all the other software package produced data sets. So if you're reading a SAS data set, that's good too. MI tools is a library. I'm going to use that to combine. Library survey is the one that I'm going to use for doing the survey data analysis. So here I'm reading in the SAS data set. into this, and then save it as an OR data file. And this impute command is exactly the same as before, because for the IVUA, it doesn't matter, because all it needs is what's the input data set and what is the output data set. If it automatically is RDA, then it's going to say that, oh, it's a R data set. So it's going to read the R data set. And then it's going to save as R data set, because you're asking them within the R toggle. So you're doing that R toggle, so it's assuming that everything is R. So the data out is you're saving exactly, these commands are exactly the same. I just copied and pasted that. And then you end impute. And then now once you have imputed it, it creates this object called oneImp in our object. It has lots of information about the information that is needed is the imp, what is imputed data set. So I'm that oneImp.rda is the object that I'm going to impute. I'm going to load. That's the imputed data set. So I loaded that into it. Then I always make a copy of it. I don't want to tinker with the original data set. So I'm making just a copy of that. And then now I create the undiagnosed as I did it in SAS. So I'm creating in the data, I'm creating a new variable called undiagnosed. And then here is the command for doing the creating the undiagnosed. And then I'm asking the education to be treated as a factor. And then in order to be consistent with what I did with SAS, I want the reference categories to be 4. And then a reference category to be 3 for the marital status, reference category to be 3 for the poverty status. And then now I have to define what my survey design variable is. So in the survey package that's called survey design, which says that what is the PSU, what is the strata, and what is the weight variable, which data set that contains that information, and then nest is true really means that the cluster indication changes, resets. So sometimes you have a strata, you have a stratum cluster 1 and 2, strata 2, cluster 1 and 2. So it's kind of a nested. So you want to say that the variable is nested. Cluster variable is nested within strata. And then now I'm going to split the data by the imputation. So this is something we had to make change here, because the R didn't like underscore mult underscore. So we had to really drop that underscore. So mult underscore is what is indicated as a different data set. So that's kind of a uniqueness of the R. And this is the option that is not needed in this case, but this is the option that you want to know, is that suppose that you encounter a stratum with 1 PSU, then it just doesn't know what to do. So in that case, I think we say that, well, treat that as a certainty stratum. So you just do the analysis of that as a certainty stratum. So there are adjust is another one that means collapse and so on and so forth. So there are other options available. So the MI results is that you apply the logistic regression on every data set, and then MI tools is MI combine is just simply to combine the results from the producing this object MI results and get the results, and then display the summary of the results, and you have a closeout R. So once you submit, then IVUware knows that everything has to be run in R. It runs R. Then as soon as it encounters impute, it executes imputes, brings it back to the R. As soon as then everything is R, and then close out R and produces the results. Now, all this credit for creating these kinds of wonderful program goes to Peter Solenberger, a super duper programmer, C programmer, Fortran programmer, who has since retired, but he still contributes occasionally to these programs. So it gives you the multiple imputation combined results. And I find that the results to be somewhat different than what we got from the survey, from the SAS. So IV-UVA regress and SAS survey logistic MI analyzed point estimates are exactly the same, but the estimates from R was different, and I don't know why they are different, so I haven't done the deep dive. And I find that sometimes R and SAS don't agree, and this difference is larger than usual, so we need to know why it is not agreeing. I'm at least glad that IV-UVA regress and SAS survey logistic MI analyzed agree. So, but IV-UVA uses the jackknife, whereas SAS and R both use linearization techniques or Taylor series techniques, so they may be different. Here's an example of running in SAS and R. Now, in the interest of time, I would say that this is a kind of a, if you were just doing a standalone version, and IV-UVA is sort of a limited because there's no recoding features available yet in the IV-UVA standalone version. So you can't create new variables. So you have to go out, create new variables and come back. Here is an example where I'm imputing, but I'm running a multinomial Rogit model where I'm predicting the who are the people who are reporting undiagnosed diabetes as a function of these covariates. So that's a completely different multinomial Logit model. I'm giving you an example of if you were to run just completely within, no software needed, just a standalone version of the IV-UVA. Now, this is the thing that I talked about, the synthetic population, where I created the 25 samples of S and 5 samples of B, and then 5 imputations I'm doing. So a total of 125 synthetic populations are created. Each one of them is imputed and then combined, and the analysis. This code is essentially using the SAS version and then but doing it. This is very, very intensive, computationally intensive, because it generates 625 data sets, and all of them have to be processed, and it may take, hours or not days to run that. And then this is the kind of a program that's a fit logistic regression model 625 times, and then computes those mean and the variance, and then computes a confidence interval for each variable in that data set. So I've given you the code for doing that, exactly replicating what I have described in that slides, 66 to 69 workshop, or 67 to 70, I think, in the workshop part 1. So, so this will take several hours or even days to run, but eventually if you run, this is the output that you get, is the variable, and then theta MI is the average of the theta estimates, standard error, and then you get a lower and upper confidence limit in this one. And you can see that this is somewhat more point estimates are very similar. Standard estimates are somewhat smaller. It's more efficient because the Taylor series, a jackknife or asymptotic. Here we are not using any asymptotic here, and it gives you sort of a 95% confidence interval using the T interval, T distribution. So this is the output that you would get if you run that program. So with that, I think we've come to the end, and I'm happy to answer any questions that you may have. And you may, if you have any other software package like Stata or MIs in Stata will do exactly the same. You can tailor it. Mice in R, you can use it. So please put your questions in the chat or raise your, if you have recommendations.
We did have one chat question come through. Let me know if you want me to read it, or it's quite long.
Yeah. Yes, this is in the longitudinal data set, when you have these kinds of people entering into the into different ages. Normally what we do is, in that case, you impute the values, because in order to maintain the correlation, you have to include all the variables. So you impute the values, but then reset them to missing values, if you don't want user to use the imputed values as the in their analysis. Does that answer the question? So the same thing appears when you have multiple children in the household, and you have some variables you are collected on this household. Now you have some households have no children; they are not relevant. You can restrict it to have children. Some households is one child. Some have 2 children, 3, so on. So the way to deal with that, if you have enough sample size, you can then partition them into children with 1 child, families with 1 child, families with 2 children, and so on and so forth. But if you don't, then the problem comes in is that you kind of impute for the non-existent children in order to make sure that you have exploited all the correlation, and reset the imputed children to missing if they are not applicable. So that's another complication that comes in when you have when you are looking at the household data with the varying number of records. Yes, Raphael.
Hi, Raghu. Can you hear me?
Yeah.
Thank you for the great workshop, as always. I was just wondering if you could speak a little bit more about the importance of variable selection, like on these imputation models, because I think on one hand you kept saying that like we should condition on all observed variables, right? But at the same time, I think at some point you mentioned that variable selection like follows similar ideas like to weighting adjustments, and we know that if we use variables in weighting adjustments that are not correlated to the survey outcomes, we are just adding noise and it just increases the standard errors and sampling variances. So I was just curious on like how that works on imputation and like the importance of like variable selection for that.
Yeah, that's an excellent question. But that's the thing is, if you want to maintain the structure in the data set, then you are better off conditioning on as many covariate as possible. As an imputer, I don't want to bias the results towards a null for any finding that user want to do. So therefore, from the imputation perspective, I want let people discover whatever is in the data set I'm trying to help them to find whatever discovery they want to do using all available information in the data set. So from that perspective, I am not looking for parsimonious models. I'm looking for models that are good fitting, as big as possible. From that perspective, yes, I should use all the variables as possible. But there's a practicality issue. So I have a data set with 500 people, 7,000 variables. There's no way I can fit a regression model on 500 people with 7,000 variables, right? So I have to do some model selection there, some variable selection there. So therefore, you can say, well, let data decide which variables are best predictors. So I use that minimum R square is one of the key features in IVE, where you can specify what's the minimum additional R square that variable explains in a regression model. So normally I try with very small number, like 0.01, 1% additional R square. And even that, if I can't fit that, also then I take 5%. So I also sometimes I use a rule of thumb is that one predictor for every 20 observations. So, 25 predictors maybe. So as I said, max spread is 25. That means it will choose the 25 best predictors for that regression model. So those are kind of a practical considerations that you have to really, it's a case-by-case basis. There's no uniform rule. The other way of doing that, which we haven't implemented, is to sort of do lasso or some other way of shrinking the beta coefficients so that you're using all the variables, but you're using ridge regression in order to get away from the collinearity problem. So, which we haven't implemented in IBE, or we haven't investigated that. That's another method for doing that. Some variable selection will be necessary if you're dealing with large complex data set. So, for example, if I take PSID, if I have, that many years of data and line up everything and then say, oh boy, I have to impute, that'll be in thousands of variables. So I have to do some imputations. Now in longitudinal data, I think that's a complication is that you have to be conditioning on the previous wave. So you just impute the wave 1, then wave 2 condition on wave 1. Wave 3 condition on wave 1 and wave 2. So you can also use principal components to kind of do the dimensionality reduction. So those are all kind of strategies case by case you have to do in order to sort of use the maximum information that is available in the data to develop the imputation model.
Okay, makes sense. Thank you.
Okay, any other questions, comments? Anything in chat I haven't answered? If you think you can raise hands or you can unmute and talk.
Yeah, I'm not seeing anything else in the chat. I think we're clear there.
All right. You're exhausted then. All right. So now you have all the software. People used to give me excuses. Oh, it's so hard. It's nice. The software is not available. Now it is not the case. So everywhere is available. Lots of books are being written on those things too. So thank you for coming, and hope that you found something useful. And if you have any questions, please feel free to email me and try to answer the questions.